So, we're going to explore the interaction picture today. A quick recap. The Schrodinger picture, we saw that states evolve, operators don't. And in the Heisenberg picture, it was the converse. Now in the interaction picture, we're going to do something, a third possibility. In some sense it's in between. We're going to allow both states and operators to evolve. Okay? And the reason for this is that the interaction picture works best when you have potentials that are time dependent. And as I pointed out in the last class, this is the most general possibility out there in nature. Right? It's not very common to have problems that are completely boring and potentials that are just dependent on spatial coordinates, have no time dependence. That usually doesn't happen. Despite that, the rest of my course will focus on such problems, right? And it's only in the third course in quantum mechanics, that is something you'll encounter next semester, where you will actually see how to put this technology into action. But the syllabus needs me to at least set this up, set the technology up. Right? So I'll set the technology up, and I'll tell you roughly where it's going to work, and I'll also, more importantly, tell you when it's not going to work. That's also very important to understand. So the way we're going to go about this is to do a separation of the full problem, okay, the full Hamiltonian, into two parts. That's what's shown here. So there's one part which we write down as H0, and let's say this is the total time independent part. In principle, H0 can have some pieces of the potential in it as well. Those pieces of the potential that are time independent, okay, they could be dependent on spatial coordinates, but have no time dependence. We push those in here. The rest we keep within a term we write as V of t. So that's the time dependent potential that we need to treat. And in principle, V of t can make for an extremely complex problem. There's no guarantee that V of t will be simple. But we do make one assumption that H0, that's something we know how to tackle. God forbid, if H0 is also something that you have no clue how to deal with, then even this interaction picture won't help. So for starters, I am making an assumption that I can, out of the total Hamiltonian, I can take out some piece which I know how to solve exactly. Exactly meaning all the technology you've learned in quantum mechanics till now. Use the Schrodinger equation to get all the wave functions and eigenenergies of H0. Yes?
By exactly knowing how to deal with H0, does that mean we can get the exact expression of the energy eigenvalue?
That's the point. So that's everything that you've learned till now. Right? So that you should know how to do. Now, most of the time this is possible. Why? Because no matter how complicated V of t is, the simplest H0 you could always choose is just the kinetic energy piece. Okay? That you always know how to solve. It's not clear, however, that that choice will be a good one. And right, hopefully at the end of this discussion, I will point out to you a spectacular example in the field of condensed matter physics, where such a choice did work, and also why that choice is now beginning to fail. Alright? So I'll come back to that at some point. So let's assume that we know the eigenstates written in this fashion, get m, such that H0 at some m, I get an energy eigenvalue E sub m. Okay. So let's say we know. Good. Alright. So as we discussed in the last class, the complication of V of t is that it's going to cause transitions between these ends. And these transitions in some sense, are going to start mixing these states. Alright? But we still want to be able to solve the problem. What does solving the problem mean? Solving the problem means that how would you determine how some arbitrary state vector alpha, okay, evolves in time. So for instance, let's say time t equals to 0, you started with this general state vector. Okay. So it's some linear superposition of all the eigenstates of H0. In general, this is what you would typically get in an experiment. And it's got some coefficients. Those coefficients are the probability amplitudes. You take the mod square, and then that gives you the probability. Okay, good. Now, the challenge of the interaction function, the interaction picture is the following. If we start with such a state alpha at time t equals to 0, we wish to find those coefficients, C of n, as functions of time such that even at some general time t later on, okay, the state written in the Schrodinger approach, okay, is still this object on the right. Look very carefully at that, okay. So it's got the same basis, n of H0. It's got the time evolution phase factors e to the minus I en p by h bar, which you would expect coming out of H0 anyway, right? The Schrodinger technology would have given you these phase factors anyway. The only non-trivial time dependence is now in those coefficients. Yes?
Sir, you are saying that all those basics we are taken.
Yes.
So those are coming from H0.
That's right.
So right. So at equal to 0 you have V0, right? But why aren't you calculating?
No, so the point is that I'm assuming that I start with such a state. That I can always do. Now I started with some general state that was written in terms of the basis of H0. I can always make this choice. Now I'm saying that if I now evolve forward in time, the action of this interaction potential, right, which is time dependent, it should still keep me in a state which is still possible to write in terms of the basis n, okay, with phase factors that would come out of which would have come out of H0 anyway, and just the coefficient C of n should now change with time.
So it is now encountering VT also.
That's right. So that V of t will only change these coefficients. No. So that is the strong assumption being made in this interaction picture. This is not guaranteed to work. Okay. But let's ask ourselves when this will work. We'll come back to that. Alright? Good. So clearly, this thing is written in such a way that at time t equals to 0, I should be able to go from here to here. Right? That's a very straightforward thing. But this assumption is a strong one. There's only these coefficients that will evolve with time due to the action of this time-independent interaction potential. Okay. Now, the way the state has been written, given that the non-trivial time dependencies have been put into these coefficients, it's very easy to see that if I want the probabilities associated with these members, each member, then that just comes from taking the mod square of any one of these time coefficients. Okay? And unitarity is still very much on board. If I sum over all these probabilities, that's still going to add up to 1. Okay? So if this works, it will work perfectly because unitarity is on board. Okay? So the choice, you could say, is a smart one, but it's not guaranteed that it will work. Right? But if I make this choice and if it seems to be working, then it will follow the rules of quantum mechanics just perfectly because unitarity is on board. Okay. So now, in order to make further progress and look at this time-dependent state in the interaction picture, and here now, I put in a subscript I with the ket. So, till now, I had above here S. This is to denote the Schrodinger picture. Okay. When I put in I, that's going to denote, that subscript denotes the interaction picture. In order to this thing, make progress into the interaction picture, I define the time, the state in the interaction picture as follows. No, this is a definition. I take that time evolved state in the Schrodinger picture, okay, and I multiply it by this phase. So that's a definition. This phase, note however, is non-trivial. It's not H that is sitting in there. It's H naught. Okay. So that's a very specific choice. Okay. So that's a definition. Clearly, if I set t equals to 0, then these two states become equal to one another. That's one nice advantage that we have. We'll see what more this gives us. Sorry, you're too late. Okay. Yeah.
So what if due to the time-dependent potential,
Yes.
there are some particles coming and going, then the probability may not
What do you mean
be
particles coming in and going? What do you mean by that? Please specify your thought a little more clearly.
like no one single state is
I've chosen a state. Are you saying that that choice is not allowed?
why
Why not? I can always prepare a state if I feel like. There is nothing that stops me from doing that. Now, whether that state, let's say some time t, call it 0, time t equals to 0. Now, how to evolve in the presence of such an time-dependent interaction potential, that's the question we're asking. Nothing tells me that I cannot make that choice. Yeah. Especially given that I believe that I know how to solve H0 exactly, then preparing it in some general state, which is written in terms of the eigenstates of that H0, that's a very smart thing to do. So therefore, that choice is also well sort of motivated. Yeah? Yes.
Showing the picture,
Yes.
the wave function can be separated into duration and time parts. So the time factor, the phase factor.
That's for a time. That's for a time-independent perturbation potential. Right? A time-independent potential.
But in the vector space picture that we're using, vector spaces, how does the time factor come?
In the same way, if that potential is independent of time, then in the very same way, through these phase factors, which are written here, these same phase factors.
Basically just to cancel it out.
So you can see that basically by putting this guy in, what he's pointing out here is quite smart. By putting this guy in, what am I doing here? Look at what this guy already had. It already had certain phase factors with a minus sign on top. What have I put in here now? So when this acts on it, what will it give me? It's removing those phase factors. Good, smart. All right. So that was my definition of the interaction state vector. Time evolved. Whether this definition is a good one or not, we'll have to revisit it. But that's my definition. What about operators? What do I do with operators? Since this is neither the Schrodinger picture nor the Heisenberg picture, there is nothing that tells me that I cannot or should not do this or that. Indeed, the operators that are related to observables here, the way they define in the interaction picture is as follows. I take some general object, some operator, in the Schrodinger picture. Remember, this guy would not have time evolved in that picture. And I put in these phase factors on two sides. Okay? So which means that with this, a time-dependent potential also, in the interaction picture, that potential will just have these operators on the two sides, these time evolution operators. But by the way, look again, which time evolution operators are we putting in? It's not the full H. I'm again purposely putting in H naught. So then this is a departure, this is a clear departure from the Heisenberg way of doing things. Because in the Heisenberg way of doing things, which operator would you have put in? There. The full H. Okay. So I'm choosing to do things in a very particular way. And you'll see why this makes sense as we go along. So these are definitions. Okay. So remember that in the Heisenberg way of doing things, the Heisenberg state would have looked like the Schrodinger state with this phase factor. Okay. Why would I put in that phase factor? Again, to remove any phases that might have already been there in the Schrodinger state, right? And this operators, I would have had these objects sitting on the two sides, the time evolution operators, but with H, not H naught. So I've written it there to contrast that in the interaction picture, instead of having H's, up here I had H naught, here also I had H naught. Okay. Whereas in the Heisenberg way of doing things, I would have used H. Good. Now let's look at what does the differential equation that governs the time evolution of the state in the interaction picture looks like. What does that look like? Because that's something that we are very keen to know. You want to see how from one time step to the next differential time step, how does the state evolve? Okay, so that's the differential equation. So for that, we'll have to take this operator and act on this state, the interaction state. That's obvious. But what is this going to give? So why this operator, by the way? Why that operator? Because at the differential level, that's the guy that actually carries out the time evolution. Okay. And if you remember, this is also the guy which is equal to the full Hamiltonian acting on the state. Okay. Good. So I take that object and I act on this interaction state. Good. So this interaction state by definition is this fellow. It has that phase that's put in with H naught to cancel the evolution within the Schrodinger state. Okay. So how many time dependencies do I have there? I have one here, this fellow, and then I have a time dependence within the state itself. So which means that when I carry out this differentiation, there will be two places where it will appear. The first guy will just pull out an H naught. The minus sign comes from the fact that I already had an I hanging around outside and another I came from the phase. Okay. And then I'll also have this operator acting on the Schrodinger state itself. That guy, by definition, you can use the fact that that guy acting on the Schrodinger state is just a Hamiltonian acting on the Schrodinger state. Okay? You can use that. And so you can write this as H naught plus V. Okay? Is that clear? Yeah? Is anyone lost? So I can put that in. And now you can see that this H naught term coming with a minus sign and this H naught term, given that it has a plus sign, they're going to cancel one another. You might for a moment wonder, oh, but look, this minus H naught has this phase factor sitting here, but that is oppositely directed from the same phase factor sitting with respect to the H naught in the other term. But my claim is that they still cancel. Why? They commute, because that phase factor has H naughts in it. And H naughts, and these H naughts down there, they're all going to commute with one another. So the H naughts in the phase factor and the H naughts down there, they will commute. So therefore, this cancellation is guaranteed. So all we'll be left with is this object, but acting on this state alpha, this thing on the interaction state. Okay. So what did I do there? I collected the fact that this guy was already acting on this V, and I purposely wrote this Schrodinger state in terms of, I just took this to the other side. Okay? That's how I get this entire, these two phase factors sitting with the V. But I know what that is. That is the interaction potential. So I get now, I get this surprising looking result coming out. The way the state evolves in the interaction picture doesn't look like the Hamiltonian, the entire Hamiltonian acting on the interaction state. It's as if only the time-dependent potential has acted on. That's V of I. Okay. So now you can see why those H naughts were put in there. Okay, in order to get this result. So what we've done here is, to give a very loose analogy, is a kind of a divorce between, well, the historical example would be church and state, or if you wish, the executive and the judiciary. There are aspects of the way we do things in life where we make clear distinctions. You do this, I do that. And of course we have to interplay. We have to be self-consistent in the sense that we should obey our own rules as well as each other's functioning. The same is being done here. We broke up the Hamiltonian into two parts in such a neat way that the states and the operators would have evolved according to H naught in that way of writing things. And if you look at the differential form for how the state evolves, it's just V of I that does the job. So it's a very neat sort of trick that we are falling back on. Yes?
This is in the interaction picture, right?
That's right.
So, essentially, what it differs when we talking about interaction picture and Schrodinger picture?
So that's what I'm coming to next.
Okay.
So the point is that if you look at this guy very carefully, you get a shock. You realize that if this interaction potential were to vanish, then the state would not evolve at all. The interaction state will not evolve at all in that picture, because it's programmed to only evolve through that V of T, not the full Hamiltonian. Okay. Now,
We are not using H naught.
no, but where even, yeah, so where the H naught comes in, look, so that's the interesting thing, that's what I'm coming to next. If you take such an operator level form for any operator in the Schrodinger and the interaction thing, those have these H naughts on the two sides, these phase factors. Now, if you look at the time derivative of such an operator in the interaction picture, okay, that guy has H naught commutator with A of I. So note how things are playing out here. In this way of doing things, there's a clear separation now. If you ask me in the interaction picture how the states evolve, I'll say, oh, V of I was doing the trick. That takes care of everything. And what about in the interaction picture, how did the operators evolve? I'll say, oh, H naught takes care of that. So there's a very clear separation. In the Heisenberg and the Schrodinger way of doing things, both H naught and V would have taken care of either the state or the operator. In the interaction picture, some strange divorce has happened. The states are evolving via V of I, and the operators, they're evolving via H0. So there's a Heisenberg-like equation of motion for the operators, but they're not using the full H, they're using H naught. And the states, they're undergoing a Schrodinger-like equation, but it's not the full H there either. It's just V of I. So a very peculiar breakup has happened. So you take care of the states, I take care of operators, as it.
Sir,
Yeah.
this is based on the assumption that we can break up H in terms of H naught and
Absolutely.
What if it is
What if that is absolutely not possible? Then you can't just apply this picture. That's it.
then how exactly are we going to do this?
God help you. I'll talk about that. I'll tell you one wonderful example where things can go wonderfully wrong, but that wonderfully wrong there's a reason I'm calling it wonderful. There's some beautiful physics there. So if you happen to get into such a mess, you might just actually have discovered something completely new. All right, but before we can come to something so exciting, let's just finish this maths. Okay. All right. So, since we continue to use these eigenstates of H0, that is this ket as our state vectors, right? So we have chosen to write, so this was the original assumption. The interaction picture, okay, has these C coefficients that are time dependent okay, and just the n, right? Why? What happened to those phase factors? E to the I, H, there was one factor like this, huh? E to the I, E, L, P by H part. But no, that was in the Schrodinger picture. Here I purposely multiplied this guy up here by this guy. So that took care of this phase factor. So that's why I've ended up with something now where it's just these coefficients that will change in time. That will take care of everything. These phase factors are now just gone. But again, I'm falling back on this description in terms of n. So, suppose we purposely multiply, let's say, this e to the minus h naught t by h bar on both sides. Let's say I purposely do it. And I want to use the fact that H0 acting on n gives me the energy eigenvalue E of n. So let me just multiply this guy on both sides, okay? So then that multiplies here as well, and then this gives me this guy, okay? So this fellow acting on this gives me the Schrodinger state, and this guy is giving me this. So this is just a cheap trick by which to show you that this statement up here, the interaction state, written in terms of just the coefficients, and the Schrodinger state, written in that way, they're equivalent. Okay. This is just to convince you of that, nothing more. So just to show you that I'm not doing anything outrageous. Okay. Now, let's do the following. Let's take this guy, the fact that this interaction state evolves using V of I, okay, and let's take the bra n with it, okay. Why? Because I want to pull out that coefficient C of n. And what I want to do is I want to know what is the equation of motion for any one of these C of n's. Because if you think about it, that's what this entire game now is all about. Because if I've written the interaction state in terms of some time-dependent coefficients and these n's, you already knew what those ket vectors were. So now if you want to know the interaction state, you better figure out these time-dependent coefficients. So I'm just going to extract those. Yeah.
Sorry to interrupt that.
No, it's fine.
So you have defined that alpha, that general state, as
Yes.
coefficient at the t is equal to 0 times the get n.
That's right.
So then you have defined the Schrodinger picture as the Cn of t e to the power. So here the Cn of t is that t is equal to 0, right? So how do you put that equivalence here? So
No, so my claim is that Schrodinger picture will continue to hold even if I apply the interaction picture. So that's an assumption. It will hold just like that. Okay? And that's what I promised I will come back to, when that will hold and when it won't. So I want to get how these coefficients change with time, because that's the only thing that I need to do now to complete the story. So the way to do that is to take that earlier equation and take the bra of n with it. So take this equation here, okay, and multiply with bra n on both sides. Why? Because if I do that, the very general state, since alpha I is written in terms of all these C of n's, it will just pull out the coefficients. It's like a projection, and which just snaps out individual coefficients. Okay. Good. So when I do that, on the right hand side, I want to do a smart trick. That smart trick is that I want to introduce a complete set of states. Okay, so I've summed over n and taken a ket bra n in there. Okay, and now you can see how this is going to go. I've ended up with one matrix element where this V of I is acting between a state m and a state n. In general, by the way, these two don't have to be the same. Why? Because I'm summing over all n. Okay, so in general, when m is equal to n, that will be a diagonal matrix element. When m is not equal to n, that's some off-diagonal matrix element. They're all going to be there. And the other thing that's going to be there, this is a time-dependent probability amplitude. Okay, so that's what's going to come up. Alright. So let's look at the matrix element. Let's do this step by step. So the matrix element, this is ket m, bra n, and V of I. So write the V of I in terms of the way it was defined. V of t, that's the time independent guy. And how is it evolving? By definition, it's got these phase factors related to H naught. But note, this H naught acting on n and this H naught acting on n, that's going to pull out the E of n on one side, E of n on the other side. Is that clear? Yeah? So therefore, you're going to get this phase factor, e to the I, En minus Em, okay, into t by h bar. And then you have this matrix element, Mn V of t. Alright? Actually, this should have been n, and this should have been n. My bad. So this, therefore, I write this n V of t n, I give it a short form. I call this V n m t. Okay? I give it this name, and that's what's written down here. Okay? So this is this time-dependent matrix element, and then I have a phase factor associated with it. So I can see very clearly. Okay? So what does that Vnm of t mean? It means that I acted with this time-dependent perturbation, okay, this potential, on some state m, and it caused me to transit into the state n. Alright, that's what Vnm of t means. I literally act on some state with this object, and it moves me into another one. Okay, and there also is a time evolution phase factor associated with it. That's this e to the I and En minus Em into t by h. Okay. Furthermore, so that's this part done. The second part, this bra m into this overlap with this interaction state, that is just, okay, that just can be written in terms of some coefficient, C of n. So I've written it for the n guy here, n bra. So that means that out here, this guy is just C of n t. That is just this coefficient. So therefore, we can see that we've ended up with this general form for how any coefficient is going to vary. It's going to be a horrible looking thing. Why? Because any such time dependence of any coefficient is going to be reliant on all other, potentially all other such coefficients, C of n, sorry, my bad, is going to be reliant on all other such coefficients C of n with weight factors given by these transitions, V n of n, which are time dependent, and then there are also phase factors. Okay. So this in principle is beginning to look awful. Okay. And I've defined a frequency omega n, which I write as En minus Em by h bar. So you might think, okay, so much maths. Can we understand this physically? Alright. So let's take the harmonic oscillator problem. Let's say you started with the system sitting in just a ground state. And this example was the one we were discussing last time. You shine light on it. Light is typically a time-varying electric field. So, and let's say the particle in that, at the bottom of that, this thing, the ground state, is a charged particle. So this time-varying electric field is going to cause this charged particle to leave that ground state with some probability. Now, which excited states could it go into? Potentially all of them. Okay? And that potentially has two things associated with it. A, the strength. What is the strength with which this electric field was kicking this charged particle? So you would believe that it would be easiest to kick it into the first excited state, right? The next one will be a little weaker, and so on and so forth. So these V and N surely will have some fall off. But there will also be phase factors, time evolution phase factors. Why? Because this kicking process started at some time and ended somewhere else, at some other time point. So there will be time evolution phase factors also. And those phase factors are associated with the difference in their energy values also, energy eigenvalues. Because you went from some initial state to some target final state. So this is how you would visualize this thing. So in the matrix way of writing things, if you bring together all these coefficients, you can write it as one column vector, C1, C2, C3, all the way down. Okay? And of course, you will have them on the other side as well. Yeah.
Because you explain the phase factor.
Yeah, so the phase factor part is just simple time evolution. The simplest, coming from the H0 part. Okay? That's surely going to come. And you started from some state which was evolving in time, and you ended up with some other state which is also evolving in time. So those two phase factors are sure to come.
But then this also depends on the energy difference.
Of course, that is the reason.
Visualize.
Well, the energy differences are the things that you knew, right? The eigenvalues of H0. So then those are the trivial Schrodinger phase factors that are always going to be. Yeah? VNM is cut, so it's no. So here, so this would be like the electric field that was acting on the charged particle. That guy you evaluated between these two states. Okay, so this is that matrix element. If you take the mod square of this might be close to some kind of intensity. But these are the amplitudes, right? And you can see that it's an entire matrix or something. You can see that this entire object is now this entire matrix in which you have these diagonal guys. What are the diagonal guys telling you? Let's say you start in the ground state, but that electric field leaves you in the ground state. Or let's say you're in the 15th excited state. The probability that that time-varying electric field left you in that 15th excited state. But surely that's not the only thing that will happen. You will, in general, move out, let's say, from that 15th excited state, come down to other states below it, whether the lower excited states or the ground one, or it could also be moved up. All of these are possible. So those are all these different matrix elements with their phase factors, the off-diagonal types. Okay. So in principle, this is a nightmare. Because you could end up with studying problems where this matrix is dense. A lot of these matrix elements, diagonal or off-diagonal, are all non-zero. Okay? That is not going to be an easy problem to solve. But physicists have been smart, and over the last 100 plus years, have figured out how to actually devise situations in which you can make these matrices reasonably simple in some context or the other. Okay. So those might be some toy model, some toy problem version of some more general real life problem. Okay. So we can learn some lessons from those toy models and then understand what's happening in all reality, in all generality. Yes.
Let's say the n or n, whatever the bases are, there are also the eigenstates of V.
If you get lucky there,
so the VNM then
so
it's
then they will all be zero.
If they are not.
No, but why would you? If they're all eigenstates of V as well, then you will stay there, no?
So it will pick out that coefficient if you do VNM. Okay.
No, what I'm saying is that if those states are also eigenstates of this V, this V of t, then why would you transit from one state to the other? You never transit from one state. All the off-diagonals will just vanish. But that, my friend, is almost unlikely to happen in real life. In general, these time-dependent interaction potentials will always start kicking you off. In fact, when you did that divorce in the Hamiltonian, that's what you typically had in mind. And let's say I know how to solve H0. It's time independent, I know how to solve it. And V of t is actually going to start mixing these. So it was programmed. Yeah, but if it doesn't, wow, thank you. I just have diagonal matrix. Yes.
So you said the electric field will interact
With the charged particle. Typically it will, no?
let's say an electron.
Yeah.
in an atom.
Yes.
But don't you know that it will be quantized like a particular frequency energy?
Right. So that's why En minus En, look at this formula. You only get certain frequencies. You can't get any frequency.
Energy.
Huh?
If we know the energy,
Yes.
the probability of that going through multiple states will vanish. Because it has a particular energy.
No. In general, all of these will be allowed. Why? What is so special?
Like
It depends, of course, on the form of the electric field. Sorry, could you share it with everyone, please?
I'm saying that his problem might be that he's saying that the light source,
Yeah.
electromagnetic energy,
Yes.
so the gravitation
can't transition to echo also.
No, I'm thinking about a time varying thing, which means it's like a pump. It's like a constant pumping of energy.
You would say inelastic transition.
So the inelastic means you're changing energies, right?
By factor that's not already explained. That's by a very
No, if it's not, those guys are not allowed out here. You can only transition into states that exist, right? But in general, the electric field could access all of them. Unless you've chosen that electric field in such a way that it's resonant with only one of them. Let's say Q. But let's say your electric field has all these frequencies in it. Let's say your electric field, you did a Fourier decomposition, and all these frequencies are sitting in there. Then can you forbid it? No. Now, who is to tell you that the electric field it must have only that one? It won't. So this relates to that toy model thing that I was talking about. Let's say you are smart and you know that in your laboratory you can cook up such a context that you'll only choose an electric field with one frequency, right? One member of the spectrum. But does the spectrum of photons have only that one frequency? No. So if you shine light, you'll have all of them.
So in this case of photoelectric effect, then you say that HGO.
Yes.
So a photon also is like.
So that's because in the photoelectric effect, they chose the light coming from some particular source with only one frequency. If they were to shine white light, all of them will wake up. Why not? Right? Of course, those frequencies that don't match any of these En minus En, they won't do anything. They will not get absorbed. But anytime one of these En minus En is met, conditions is met, that transition will happen. Yeah? Sorry? No, the diagonal elements are by definition not transition. Because it is just, you start from that state, you stay in that state. Definition. So now we come to that last part. When is it safe to assume this? And when will this break down? Okay. So, not too many of the books actually talk about this. You have to look very carefully to figure this out. But the point is, what we're asking here is something very subtle. When is it safe for us to choose that eigenbasis of H0? Or another way, when is it even safe to break up that general Hamiltonian into some H0 and some V of t? When is that even safe? Okay, so these are tough questions, right? But it turns out that there is a simple answer, and the simple answer is the following. Let's say you could make this divorce in principle. Let's say it's allowed. Okay. If V of t does not cause the ground state that you start from, the H0, to after some time, after the application of this V of I, this time-dependent function, if it transits into a new ground state, which is completely orthogonal to the one you started from, then in that case, this interaction picture is just rubbish. Okay? Because at some point what will happen is that as you apply this time-dependent interaction potential, this initial ground state that you had will undergo some kind of a level crossing with a new ground. Okay? They will become degenerate at some point. That degeneracy is something that you will not be able to handle from within this picture. That degeneracy is like a singularity, which cannot be tracked from here. Okay? So if you start, so the idea is that this is a kind of benign, this interaction picture is very benign. What it says is that when I start up this interaction potential, V of t, I should take my spectrum, all those ketons with their energies ENs, okay? And I should be able to move into some new states which have a similar ordering of the spectrum, which means that these states don't get interchanged. The ordering remains the same. Maybe they can get pushed up or down a little bit. Okay, so imagine that you initially started with some tower of states. This was your ground state E1, then E2, etc., etc. Okay, so this was at time t equals to 0. You applied this v of t. My claim is that the interaction potentials, this picture still works as long as I have the same E1, E2, E3 thereafter. Okay, and especially true for the ground state. If that doesn't happen, then this passage involves a massive shake-up of the system. Okay. Because there will come some point during the application of this V of t where this old E1 and the new ground state, they will become degenerate. They will be the same, the same points in the spectrum. Okay. That is not something that this guy can handle at all. Right? So let me give you an example of this. A wonderful example of this comes in the field in which I work, condensed matter physics. And the thing goes as follows. Imagine a piece of metal. It can carry current from one end to the other. Okay? We know how that works. But there's a trick. Electrons all interact with one another, the Coulomb force. So even though you're pushing, using an electric field to push electrons from one end of the system to the other, that's how conduction works, by the way. Okay? How do you know that these electrons aren't going to start repelling one another and do something crazy? After all, if you think about it, there are 10 to the 23 of these electrons in a small bit of the metal. Okay? Tiny bit. Something like a few grams of that metal. There are 10 to the 23 electrons. You're trying to push them across the system, but they're all repelling one another. And by the way, that repulsion, if you really take it seriously, that falls off as 1 by r. So if you take typical length scales in a metal, what are the typical length scales that you consider in a metal? Can somebody tell me? Some bright spark. What are the typical length scales we should consider? Yeah, take a copper. Huh? Centimeters. Is this a sensible length scale for the electrons, my friend? No. So tell me sensible thing. For you it looks sensible. Because you couldn't make something which was much bigger or much smaller, right? Now let's think in terms of electrons. What's a sensible length scale for them? Femtometers. How much is that? 10 to the minus 15. My goodness. That's really short. Well, you undershot it. You've gone, you like overachieved, you really underachieved. Anything else in the middle? Should make a compromise. Angstrom, nanometers, 10 to the minus 9. Even if you tell me microns, 10 to the minus 6, which is like the width of a hair. You take out one strand of your hair, you can still see it. That's roughly like 10 microns. Okay? So it turns out that 1 nanometer, 10 angstrom, roughly a typical good length scale for us. But this is like a crowded bus, right? Because you have 10 to the 23 electrons all jostling about on these length scales. So aren't they going to bump into one another? This is going to be one bumpy ride, right? Even if you've got this electric field telling them where to go, either say, udhar. But even then, right? Imagine, it's going to be stampede because they all repel one another. So then how does nature work this out? Because we know that there are conductors out there that are pretty good. So how does nature work this out? Okay, so the Russian physicist Lev Landau figured out how this would happen. And his idea was to use the interaction picture. Because what he said was something amazing. So if I were to ask you the following. Suppose you have this crowded bus of electrons and they're all repelling one another. Would you expect that the result of all of these interactions is effectively to have no interactions at all? Would you believe me if I were to tell you that? 10 to the 23. Would you believe me if I were to tell you that too many interactions is like having no interactions at all?
Because the interactions in themselves they will be random.
So
it's like on a large scale, they will cancel out.
But that means nobody will move, no?
No.
Because you don't want me to move forward, let's say you're in front of me. Somebody in the back is saying you can't come back. Somebody to my left and right is telling me you can't move. So what will I do? Just get frozen. So the electric field, I'm not going to move. 10 to the 23 neighbors of mine are telling me not to move.
The interaction with the neighbors are zero.
Huh? All the neighbors can move together.
Yeah.
Okay, but what happens to all the repulsion? So this electric field is overrides all of that.
Just try to like sympathetic response, right? So some of them are moving let's say
And the rest?
let's say like more than half moving in a general direction,
Huh.
and the rest are not.
Why?
Then no,
Why?
if you start with random
No, okay, you can start with that. You tell me in your random configuration, how will these becharas handle all the repulsion they're facing? Remember, it's repulsion, it's not attraction. If it was attraction, then everyone moving together, I can imagine, in one beautiful motion, because we all love to be together. But they all hate each other.
So then try to find the low energy configuration.
And that will be just stay still. Minimizing repulsion means just stay still, right? Hiloma.
So all electrons may not need to go from one end to another.
Arey boss, the electric field is telling everyone, move. It's like me telling you guys, sit.
But it's like just one person giving a push in a crowded bus and the information.
So who is this guy? The Incredible Hulk? This one guy pushing and everyone is Chikakinikla. What are you saying? It's just one electron and it has to move 10 to the 23. Surely it's not going to work, no?
You guys are just moving out because if you've defined a certain space where there's some boundary.
Okay, so in that crowded bus, this boundary guy will basically to climb on top of everyone and move through there and out. Really? Tried it in a bus? Dada ekku daran. It was. Oh yeah, right. Jumte padenge aapko. No, that's not how it's going to work. Okay, so wait. I'm sure we can all come up with interesting possibilities. But what Lev Davidovich Landau showed us is that there is a magical way in which this all works out. It turns out that there's something called screening that happens. Okay? Screening basically means, very vague thing, is like some of you guys are guessing it. Since there are so many guys who are all repelling me, right? The net effect of all of those repulsions gets weaker. And all that effectively matters at the end of the day are my immediate neighbors. Okay? Something beyond my immediate neighbors, I don't really need to worry about them at all. Alright? It all magically works out that way. Alright? And the strength of this repulsion all becomes much weaker. And so much weaker that I can imagine this system as being effectively non-interacting. Just a gas of non-interacting electrons. Now, non-interacting electrons will face electric field. Chalo, move. Everyone moves. There's no repulsion to stop them. Landau's assumption was that something like an interaction picture should work. Okay, so he assumed that, carries out a calculation, computes certain things from his theory, checks it with experiments, and finds that his predictions are matching the experiments, and vice versa. Okay, that's a miracle. Now, 40, 50 years, 60 years down the line, we understand that it's not really a miracle. There were some things that he was assuming which can be derived. There were certain axioms he had in mind which can actually be obtained from much more powerful methods that Landau didn't have. So his genius was that he was able to kind of make some simple-minded assumptions, go forward with it, he had the courage to do it, and it really seemed to work. But it also turned out that since the last 30 years or so, people have seen in the laboratory many examples of metals which don't look like this thing that Landau cooked up. There are all kinds of metals which are much stranger. Okay? And those people have been trying to figure out why do those metals come about? And this is the reason. The interaction picture breaks down. There's usually a huge shake-up because of the interactions, which is so strong that picture, the effectively non-interacting gas of electron picture, is just blown to smithereens. What comes about is something very difficult to imagine. I could not begin to explain it to you here. You just don't have the sophistication to understand anything that I would throw at you. So, pardon me if I can't do that. But that's the kind of, craziness that can break down. So, some of you were asking, what would it mean for this thing to break down? Another way of putting when this works is adiabatic continuity. That phrase, let me repeat, adiabatic continuity. What it means is if I start a V of t in the system very slowly, infinitesimally slowly, from minus infinity to plus infinity, gradually, okay? Will this basis n Keten of 80, will that remain good through every step of this introduction of V of t? That's the assumption that's been made. So what it means is that at every step, while I introduce V of t, that basis, that entire tower of states should stay in place. It should not break down. Okay? So across this slow introduction of V of t. If you think about it, that's a pretty radical thing to be assuming. There is no guarantee that that has to be the case. Landau's genius was that he showed that that can obtain in a certain circumstance, and when it does, it describes a huge class of things. Okay. He won Nobel Prize for something along those lines. He could have easily won more than one. He was that good. He didn't have all the advanced machinery, theoretical machinery that we have today. And yet he was able to, just use the power of quantum mechanics to make these arguments. So this is roughly where it will work, if the interaction picture will work. And when it won't work, you're probably about to discover something very exciting. Okay? Because when it works, you've actually fallen back on the simplest possibility. Something more exotic is now about to come. That's what is this breakdown of this interaction picture. Okay, so yeah, so we're almost out of time for today. Any final questions? Yeah.
For those Dirac motivation for my
Well, so basically, like I explained, when you introduce V of t, how do you know what it's going to do? It could start violently mixing things, and So Dirac had to take a sort of posit that it won't. Basically, adiabatic continuity. So he was positing that adiabatic continuity would hold. And then he asked, okay, so what comes about out of this? So maybe 2-3 semesters down the line, some of you are going to study quantum field theory. When you do, this is going to come back in use, because in many of those problems you're going to end up asking yourselves that if I have, let's say, a non-interacting system of electrons, put in interactions between them, or let's say I have various kinds of quarks and I put in interactions between them, what's going to happen? I mean, the thing that Landau discovered for metals, the same thing is actually true even in quantum chromodynamics, where if you start with instead of having the simplest kind of metal, there what you do is you start with something bizarre called the quark-gluon plasma. You start with lots of quarks of various kinds all floating around, and you have the gluons, which are supposed to actually, bring about interactions between them. But this is some kind of plasma, right? These quarks are not really doing anything. But then, as you lower temperature, we know that in our universe, you end up with protons, neutrons, various kinds of hadrons, mesons, whatever. Where did that come from? It turns out that the system, the interaction picture of the quark-gluon plasma would have broken down. So those events are what we call phase transitions. Okay. Typically, some kind of a phase transition must have happened in the universe as the universe was cooling down, and these bound states called protons and neutrons started forming. Okay. So that magic is something that we don't completely understand. People are working on it, okay? But QCD is one of the hardest problems there are out there in the field of high energy physics. And so some of you might actually go on to look at those. But at the basis of much of that will still be these humble ideas from quantum mechanics. When it works, it's the interaction picture that's going to work. When it breaks down, it's this picture that's going to break down. Any last question? Yeah.
In a matrix representation,
Yes.
we consider one coefficient, say like 0 degree of C.
Yes.
So it would be a linear combination of
All of them. So C3 means you'll have all these fellows multiplying all of these guys.
Yeah, so basically we would have the C3 being
So that's the probability to stay in a state.
There are terms that are forward evolving in time and there are terms that are backward evolving. So what does that mean?
In general, it's all allowed in quantum mechanics. You can time evolve one way or the other. In the Newtonian world, we don't see that. But in quantum mechanics, this is not forbidden. It's going to be there. Whether you like it or not, it's going to
I
be.
mean, like, what does that actually mean? How are you like considering her coefficients that are like that?
We'll come to that at a later point in this course. We can discuss it outside, but I don't want to get into the discussion here because that's an important part of something that we will study ahead. Time reversal symmetry. Next.